Hello viewers, welcome back to the course on scientific computing using MATLAB. So, in the previous lecture we have started with the Simpson rule and today we will continue with that one. So, in the previous lecture we have started doing the integration for the function from a to b f(x) dx, and then we have approximated the function f(x) with p2x dx plus the error terms. So, this one we have started with. Now, then I know that the p2x was the second degree Lagrangian interpolating polynomial, that was x is equal to x1 and this is equal to x0 x2 x1 minus x0 y1 plus this is x minus x1, x2 minus x0, x2 minus x1, y2. So, this is we have started. Then we wanted to do the integration of x0 to x2 of this factor. So, this factor we started with the transformation, that is x is equal to x0 plus ph, and then dx is equal to h dp. X minus x1 can be written as h p minus 1, x minus x2 can be written as h p minus 2, and so on. So, this is we have done in the previous one. So, from here I can write down that this integration. So, y0 can be written like this: x0 minus x1 is minus h, x0 minus x2 is minus 2h, and inside I will get x minus x1, x minus x2 and dx. So, this part can be written as y0. So, minus and minus, so it is 2h square, and this one I can say that when x is equal to x0, p will be 0, when x is equal to x2, p is equal to 2. So, from here I can write that this is equal to h p minus 1 into h p minus 2 and dx is h dp. So, this value I am getting. So, from here I will get y0, h and h. This h I can take common. So, I can write h cube by 2h square from 0 to 2 p minus 1 p minus 2 dp. So, this integration I need to find out. So, this h square will go with this. Now, from here I can write that this is equal to y0 by 2, and then integration of this one. So, this is 0 to 2, I can write this as a p square minus 3p plus 2 dp. So, this will be equal to y0 by 2 into h. So, this h will come, and then I will do the integration of this one. So, this will be p cube by 3 minus 3p square by 2 plus 2p from 0 to 2, and if I put the 2 here, so this will be y0 h by 2. So, this will be 2 raised to the power 3, that will be 8. So, 8 minus 8 by 3 minus, so it will be 4, so 12 by 2 plus 4 minus 0. So, I will get this value, and from here you will see that this is the 6 LCM. So, if you see this one, I will get the value y naught h by 2, and inside I will get 8 by 3 minus 6 plus 4, 8 by 3 minus 6 plus 4. So, it is minus 2. So, it will be y naught h by 2. So, this is minus 2. So, minus 6, 8. So, it will be 2 by 3. So, this will cancel out and I will get h by 3 y naught. So, I will get this value. Similarly, I can go for the next integration from x naught to x 2, x minus x naught, x minus x 2, x 1 minus x naught, x 1 minus x 2 and y 1 dx. So, this I will get, and from here the same way we can find out. So, this will become y 1, I can take common, this will be h, y x 1 minus x naught is h, x 1 minus x 2 is minus h, right, from 0 to 2, x minus x naught is ph, x minus x 2 is p minus 2h, dx is h dp. So, I will get this value. So, from here I will get minus y 1 over h square, this h will come common. So, multiply by h cube from 0 to 2. So, I will get p minus 2 dp. So, this is the integration we are going to get. So, from here you can say that this will be minus, so this will cancel out with this. So, it will be h y 1 and then integration, this will be p square. So, it will be p cube by 3 minus 2 p square by 2, 0. So, minus h y 1. So, this is 8 by 3. So, this will cancel out, minus 4. So, this is, so it is a 12 minus 12 plus 8 minus 4 by 3. So, this will be minus h y 1 into minus 4 by 3, right. So, from here this will cancel out. So, it will be 4h by 3 y 1. Similarly, we can find out x 0 to x 2, x minus x 0, x minus x 1, x 2 minus x 0, x 2 minus x 1, y 2 dx. So, the same way we can find out by all this substitution. So, it will get the value here, this will be y 2 divided by 2h into h, right, from 0 to 2. Now, x minus x naught is ph, x minus x 1 is p minus 1h, then h dp. So, it will be y 2 into h cube by 2h square from 0 to 2 p minus 1 dp. So, this will cancel out, and if you do the calculation again, so it will be y 2 over 2 into h, and the integration will be p into p square. So, it will be p cube by 3 minus p square by 2 from 0 to 2. So, it will be 8 by 3. So, h y2 by 2. So, this will be 8 by 3 minus 4 by 2, and from here it will be 2, 6, so 2 by 3. So, it will see that will be h y2 by 3. So, that is the value we are going to get. So, now from here if I take the integration from x naught to x2 my p2x dx, then this will become h by 3 y naught plus 4h by 3 y1 plus h by 3 y2. And now from here I can take h by 3 common. So, I will get y0 plus 4 y1 plus y2. So, this is the integration we are going to get when we approximate with the second order interpolating polynomial, second degree interpolating polynomial. So, in this case I am getting h by 3. So, this is called Simpson 1/3 rule, because you will getting 1 by 3. So, h by 3. So, this is a Simpson 1/3 rule. So, now from here I am getting the solution of the integral. Now, let us find out the error. So, the error in this case will be from x naught to x2, this is equal to x minus x naught, x minus x1, x minus x2, third derivative xi over 3 factorial and then this is equal to dx we are getting, where xi is lying between x0 to x2. Now, from here I can add this as 3 factorial from here. So, this is basically 6. So, I can write this as 3 factorial 6. Now, this integration I can again take the substitution that x is equal to x naught plus ph. So, from here I know that this is equal to 0 to 2, okay. X minus x naught is a ph, this is p minus 1h, this is p minus 2h and this is h dp. So, this will get. So, from here I will get h. So, 4 power of h, third derivative xi over 6 from 0 to 2. So, this will be p minus 1, p minus 2 dp, and then from here if I do the integration I will get. So, I will get here just make it simplified. So, this is p square. So, it will be p cube, it is a minus 3p. So, it is a minus 3p square and then it is plus 2 plus 2p. So, this will I will get, and now from here I will get h raised to power 4 by 6, then it will be integration p4 by 4 minus 3p cube by 3 plus 2p square by 2, 0 to 2. And if I further simplify, then it will be 16 by 4. So, it is 4 minus, so this 3 will cancel out, minus 8, this 2 will cancel out, plus 4, that is it, and this is 0. So, that becomes 0. So, in this case if you see, then the error is coming 0. So, that shows that so it means that if I choose this error, and you know that this is a cubic polynomial, if you multiply x minus x naught, x minus x1, x minus 2, so that is the cubic polynomial. So, in this case it is giving the error 0. So, which implies that Simpson 1/3 rule gives exact solution or integration, exact integration I should write, exact integration not only for quadratic polynomial, but also for cubic polynomial. So, in this case it is also giving the exact integral for the cubic polynomial. So, in this it means that it is going to give the error for the polynomial having the degree greater than 3. So, in this case what we will do? So, let us say, let us define the error So, in this case I define that the R x first. So, R x first I take x minus x naught, x minus x 1, x minus x 2 and x minus x r, that x r can be x 0, x 1, x 2 into some function of xi. So, in this case we generally take that x r we take at the middle point. So, from here we can choose my x is equal to x naught, x minus x 1 square, x minus x 2. So, this we choose, and then this is the fourth derivative by 4 factorial. So, that is the remainder term in the case of quadratic polynomial. So, now we do the integration and finding the error. So, the error in this case will be integration from x 0 to x 2 r x dx. So, this will be f 4 by 24 x 0 to x 2 x minus x 0 dx. So, let us see what will happen, whether it is going to give the error for this, because this is a, if you see, it is a 4th degree polynomial. So, now I want to find out what is going to happen with this one. Now, the same thing I will choose that let x is equal to x p no ph, then I will get my error. So, this will be f 4th derivative by 24 0 to 2. So, in this case it will be 0 to 2. Now, x minus x naught is ph, then x minus x 1 whole square. So, it is h square p minus 1 square, and then it is h p minus 2, then h dp. So, this is I am going to get. Now, from here I will get 24. So, h square, h and h. So, 5h. So, h raised to power 5 will come out, and then I will get 0 to 2 p minus 1 whole square into p minus 2 dp. So, this value we are going to get. Now, if you further solve this one, I am getting 0 to 2. So, this will be p square plus 1 minus 2p into p minus 2 dp, and this will be p square minus 2p. I will calculate. So, if you do the calculation for this integration, you can do the calculation for this the same way. You will get the value. This will come out as minus h raised to power 5 by 90, where xi lies between x0 to x2. So, this calculation you can do, they will get the 90 value. So, from here I can say that this is my error, divided by 5, 90. So, from here I can say that the error will be, so this method is going to give the error whenever we are dealing with the function whose fourth derivative is non-zero. So, it is up to the cubic polynomial, the error was 0, but if you have a function with the fourth degree, then some error will be introduced, and this is the error in the case of Simpson 1/3 rule. Now, so let us go for composite rule. Simpson 1/3 composite formula. So, in the composite formula, what we are going to do is, so let us do on the next page. I have the function. So, suppose this function is this, sorry, this is x is equal to a, this is x is equal to b. Now, I split this into the subintervals with the nodal values. So, this is my x0, x1, x2, x3, xn minus 1, xn, xn minus 2 and so on. Now, what I do is that instead of taking the one quadratic polynomial for the whole function, I will split this one into the subintervals, and then what I do is that 1, 2, 3. So, this 3 value I choose. So, this is the function I have. So, I approximate this function with a quadratic, this one. The next function is from here to here. So, I will approximate this function with this quadratic. Then I will choose this one and I will write this one. Then I will find out this value and approximate by this function, and in the end I will approximate this function by this quadratic polynomial. So, by this way we have a quadratic polynomial in the pieces. So, from here I can say that the integration from a to b f x dx. So, this is my integration I am going to do. So, this will be equal to x0 to x2 f x dx plus x2. So, x2, x3, x4. So, it will be x4 f x dx and so on. In the end I will get, so I will get x n minus 2 to x n f x dx. So, in this case one thing is that if I am to choose 3 points, so 3 points this one, then next 1 and 2 points more, so 5, then 2 points more 7. So, from here I can say that the number of points, nodal points, should be odd. So, it should be 3, 5, 7, 9, greater than 1, definitely of course greater than 1. So, from here I can say that n should be even, because when the n is even, the n plus 1 points will be the odd. So, that is the criteria. So, n should be 2m always, the even value. Only then we can apply the composite formula for Simpson one-third rule. And from here I can say that this is represented by this polynomial, interpolating polynomial. So, from here I can say that now I will use the formula. So, this is the value we are going to get. So, it is h by 3 y naught y1 y2 multiplied by 4. So, this one I am going to use. So, h by 3. So, h is b minus a by n. So, this is my h. Now, this is the formula y0 plus 4 times y1 plus y2. Now, the next interval, it will be h by 3. Now, y2 is coming here because this is the connecting node. So, you note this is the node. So, that is the connecting node. So, here I am getting y2 plus 4 times y5 y2 sorry y3 and y4. So, 2 2 3 4, then plus h by 3, then y4 plus 4 times y5 plus y6 and so on, and in the end I will get h by 3 yn minus 2 plus 4 times yn minus 1 plus yn. So, this is the composite formula for the Simpson. Now, if I collect all the terms, I can take my h by 3 common. Now, you can see that y0 here it is coming. Now, y1 4 y1 4 y3 4 y5 this is coming, y2 is coming here and y2 is coming here. So, from here I can write that this will equal to y0 plus 4 times the odd values. So, y1 plus y3 plus y5, in the end I will get yn minus 1 plus 2 times the even value y2 plus y4 y6 yn minus 2, because this is the connecting node. So, this is the connecting node basically. So, connecting node is this. So, wherever the connecting node is there, I will get 2 times of that one plus the last term, that is yn. So, this is the integration of the function . So, this is the Simpson one-third rule, composite rule for the given function. So, in this case what we will do? I will find out the h, that h we can find from here, then y0 plus 4 times we have to do this odd values, plus 2 times we have to do with the even value, that is the interior values, plus yn. So, y0 and yn, that is the boundary point, we know that the value of the function there, only we have to take the internal values odd and even and multiply by 4 or 2. So, that is the solutions for. So, this is the Simpson one-third composite rule. So, from here I can define the same way we can define the error. So, I can define the total error. So, total error I know that we can multiply by n. So, the same way I can take multiply by n into h raised to power 5 by 90 f fourth derivative xi, where xi is from x0 to xn. So, the same way this we can choose the maximum. So, first we choose the maximum error in any of the interval and then we just multiply by n. So, that will take as a total error. So, this is basically upper bound for the total error in the Simpson 1/3 rule. So, this is the formula for the total error. So, we will stop here. So, today we have discussed that the Simpson 1/3 rule, we derive the formula for that, and then we have discussed the composite 1/3 rule and the errors corresponding to this. So, in the next lecture we will continue with this one. Thanks for watching. Thanks very much.